Okay, so what we are discussing, let us briefly recapitulate. We were discussing the matrix method or finite element method of frame analysis for buckling. So we want to study global buckling of frame, and we have derived the stiffness matrix for the for the frame for the beam column element, right? So two noded beam column element, this is node 1, this is node 2, and then they have W1 theta 1 and W2 theta 2. Okay, deflection, vertical deflection and rotation, right? And then so four noded, 4 degrees of freedom. This was the stiffness matrix contributed from elasticity from of the beam column element, and then additional thing for buckling which is required is the geometric stiffness matrix. So these terms we have once again written here. Okay, then we will solve. We have also demonstrated how to. We have taken a simple example of the cantilever beam column or any boundary condition. You can consider fixed hinge, and with a single element discretization we can solve for its critical load. That we have solved, and then we have seen that whatever we have obtained from here by solving the algebraic value problem matches well with the one we derived analytically, right, in our second year strength of material class, right? Now we are going to solve a problem in which buckling of a frame. Maybe some of you will definitely in experimental method class you will verify this, okay? But I have seen that the buckling of a frame, there is one experiment designed for that. But how will we find out the buckling load for the buckling of frame? Okay, that's what I am going to demonstrate. So this is a frame, assuming that this is hinge, and then all elements are length L for simplicity and flexure rigidity Di. Subjected to this, of course there need to be compression, right? So subjected to this compression. Now we can consider, because there is symmetry, right? Symmetry. So either we can exploit the symmetry or anti-symmetry in that matter to analyze it. Okay, so it can buckle either in symmetric mode or anti-symmetric mode. It can buckle either symmetric or anti-symmetric mode. Anti-symmetry. If we don't consider, so symmetric mode will be one in which symmetric will be what? When it is buckling under a symmetric mode, then what it will going to happen? This will deform like this, right? This is the way it will deform. This is the symmetric mode, right? So then what we can see, so when it is deforming in symmetric mode, the vertical, this point, this is the axis of symmetry, this is deflecting. So here the slope will be 0, right? And there is no lateral translation, right? So there is no sway of the frame. So for the symmetric one, we can approximate it like this. We can approximate this frame something like this one, and here we can allow vertical deflection, but we can restrain horizontal. So we can provide it a shear hinge over there. This is shear hinge where the vertical deflection is allowed, but no rotation. Okay, you see. So this is the idealization. Half of this we are exploiting symmetry. Okay. So the degrees of freedom here, you can see for this one will be here. There will be W. There will be rotation. Here will be rotation. There will be rotation and deflection. So maybe here it is. If you 1, 2, 3. This way you have going to you are putting frame. So theta 1, this will be theta 2, this will be theta 3, and this is maybe W, right? This has so only 4 degrees of freedom, right? Now, if it is deforming under anti-symmetric mode, then what is going to happen? You see that this will go there, and then this will come there, and then it will something like this. Okay. This will be something like this. Okay, so this is anti-symmetric mode. Maybe something like this, and this will go like this. This will go like this, and then this will be something. So in anti-symmetric mode, what we can see that there will be a point of counterflexure here, because from the positive curvature it will go to negative curvature, right? Okay, and here 90-degree angle should be maintained. Here also 90-degree angle need to be maintained, right? So what we see here. This point will not deflect, okay? This point will not deflect, right? So, but lateral translation will be allowed, right? So, for the antisymmetric, what what kind of idealization we can consider? Explosion antisymmetric mode is we cannot allow, well, I mean, there will be, so we will allow rotation, but something like this, okay, something like this, isn't it? So you see that sway is allowed, and then we are considering only half of it. So rotation is allowed. So you can, okay, you understand that? And so this is subjected to force P, this is also subjected to force P, and then here you see that there will be one rotation, 1, 2, 3, rotation theta 1, rotation theta 2, rotation theta 3, theta 3, and please note that here there will be no rotation, sorry, there cannot be any rotation, only vertical deflection, okay, then there will be W deflection, okay. So here only 3 degrees of freedom, where there is antisymmetric mode, there will be 4 degrees of freedom, right? Okay, here the degrees of freedom of symmetric mode will be theta 1, theta 2, and W. Further in antisymmetric mode, the thing will be theta 1, theta 2, theta 3, W. Right? Symmetric mode and asymmetric mode. Okay, you see that? So you see how we can reduce the complexity of the problem. So why we are doing so? Because we want to reduce the number of degrees of freedom. So we have to solve by hand. We can write a computer program and we can solve any problem. But this one I want to show you that how we will do the element level stiffness, assembly of element level stiffness matrix to form the structural stiffness matrix. Okay. So now we will first consider the antisymmetric one. Okay. So for the antisymmetric one, how will you do that? You see the, let us theta 1, theta 2. I am going to write, so theta 1, W, theta 2, theta 3, theta 1 W, theta 1 W, theta 2, theta 3, right? Theta 1 W, theta 2, theta 3. Okay, you see that? Now let us do the assembly. Okay, so you see that this is element 1, this is element 2, that is the way we are putting. So you see that theta 1. So and this member 1 is subjected to a compression load of P. Okay, whether there the P is 0, there is no compression load, so P is equal to 0. So only this member is subjected to compression, right? Now how will you do that? So theta 1, this degree of freedom, theta 1 node 1. So which member is going to constitute in this stiffness? Only member 1, right? So member 1, what is the material stiffness matrix? Theta 1. So theta 1 will be nothing but 4EI by L, right? 4EI by L, right? So this length L, okay, so 4EI upon L, is that fine? And so that means this term, right? And the respective term here is what? 4L square P, 30L. So here it will be minus 4P L by 30, right? This is theta, okay? Fine. There is no contribution from the 2, right? Because this node has nothing to do with this, okay? This one. So that is the 4PL by 30, 4A by L. Similarly, now W and theta 1. W and theta 1 will be, look, although we are saying W here, but this W is same as whatever is the W here, right? You see, because this member we are considering axially rigid, right? So whatever W here, this W and this W are same. So when we are considering W and theta 1, what we are going to consider, it is cross stiffness, right? W and theta 1 means this is those 2 degree of freedom belongs to two different nodes, right? So when we are considering cross stiffness W and theta 1, only the member which is connecting the two node will only contribute. Understand or not, right? Isn't it? Look, this W is same as this W, right? Because this is actually rigid. Now, what we are considering, the stiffness, this whole, basically this block is between W and theta 1, right? So W and theta 1 means this is W and this is theta 1. So it belongs to two different nodes, right? Now all of you have done matrix method structural analysis, right? All of you, matrix method structural analysis. Okay, then if you did that, then only you will understand. If you didn't do a matrix method structural analysis, you will not be able to understand. So W and theta 1, so the cross stiffness, right? So cross stiffness is because these 2 degrees of freedom belongs to two different nodes. Only this member is connecting the two nodes, so only this stiffness will be contributed by only member 1, right? Because this is connected between these two nodes, right? So first you must understand this W is basically coming because of lateral deflection of this member, not because of axial deformation in this member. Because when you consider this node, this W1 theta 1, W2 theta 2, we do not consider any axial degrees of freedom. Must understand, right? So for this stiffness, W and theta 1 will be what? Well, theta 1 and W. So theta 1 this and W2 is this theta 1. This theta 1 W2 is minus 6ci by L square, right? Minus 6ci by L square, isn't it? Minus 6ci by L square, right? The respective, meaning this one, right? This one, isn't it? This. So respective member here, what is that? This one. So minus 3pl by 30, okay, minus 3p by 30, okay, minus 3p by 30, so minus 3p upon 30, right? Please know that, huh? It will be plus 3p by 30, yes, you are right. Because here, this one, nah? Yeah, this right, it will be plus, right? This one, it will be plus, that's true. So then what about theta 1, theta? You understand why this is, right? Okay. Then theta 1, theta 2. So theta 1, theta 2 will be what? Acha, theta 1, when we are writing theta 1, 4ai by L, right? 4ai by L, okay, this one. And then 4L square, 4PL square, right here. K minus Kg, okay? Okay, fine. Okay, so now what we are going to do, let us do theta 2 and theta 1. So theta 2 and theta 1 is what? Theta 2, theta 1 is, look, this is theta 2, this is theta 2, and this is theta 1. Theta 2, theta 1 is also a cross stiffness. Will only be contributed by member 1, right? Theta 2, theta 1. So theta 2, theta 1 is theta 1, this is theta 1, and theta 2 is this one, right? So theta 1, theta 2 will be nothing but 2ei by L, right? This 2ei by L, 2ei by L, and the respective member here is nothing but minus P L by 30, right? Plus 3 P L by 30, right? Fine. Now theta 3, theta 1. Theta 3 means this one and theta 1. There is no cross stiffness, right? So here should be 0. Now WW will be what? W is here. WW will be contributed by whom? Only this one, right? Because so 1 W and W. So Of course, for member 1, second node, W2 W2 is this one, 12bi by L cube, right? 12bi by L cube, 12bi by L cube, right? And for respective member here is, yes, nothing but minus 36 P by 30L, right? Minus 36 P by 30L, right? Okay. So other also you can find out. You do not. I am writing down the final things. Okay. So when I am writing here, please check yourself that minus 6ci by L square, plus PL by, P by 10. Okay, LL will cancel out. So this is 0, and then it is 4 Vi by L minus 4 PL square by 30L plus 4 EI L by 2. Let me explain to you why it is so. 2I L by 2 4EI. So here what happened is that, look, when I am considering this member, theta to theta 2, theta to theta 2 will be this one. Theta to theta will be contributed both by member 1 as well as member 2. So for member 1, what will be theta to theta 2? For member 1, it will be this one, 4ei by L. So that's what 4ei by L. And then minus this one, 4p L square by 30L, right? 30L, right? But then it will also contributed by member 2. So for member 2 there is no axial force. So there is no contribution of the geometric stiffness matrix. But the contribution of this one material will be there. So theta 1 is what? This is theta 1. So 4ei by L is still there. 4ei by, instead of L it is L by 2, because this is L by 2, right? But this, something like that. So this is the way we did. Okay. Now this has to be symmetric. So the other part term you can also write it here, symmetric, right? Similarly, I can also write down the stiffness matrix, for the symmetric mode, symmetric mode if I write, then it will look like this, 4ei IL minus 4PL square by 30L, 4PL square by 30L, this is 2 Pi by L plus PL square by 30L, 0, whatever symmetric. So this is 4 Pi by L minus 4 PL square by 30L. Well, I have to write it nicely. Here it is too clumsy. Okay. Anyway, so I will write it here. For the symmetric mode, for this one, for the symmetric one, the stiffness matrix will be writing theta 1, theta 2, and W3, W, theta 1, theta 2, W. Four EI upon L minus 4PL square by 30L plus PL square plus 30L equal 0. Okay. You please check for this one also similarly. So now we can adopt. I am removing. We can adopt typical value of this parameter. Now let us find out. So you can see that for this case, see what happened is that I think whether you have taken it positive or negative p, it will not matter, because even if you take positive, there in the result you will get it negative. So if you assume it is tensile, it will you get negative value. If you assume that it compression positive, it okay. So you solve the eigenvalue problem. So k plus kg equal to 0, and then to solve for the what is unknown. The unknown is nothing but p. All other things are known. Solve for p. Then basically solve for p. That is the that will give you the critical load p. So that is p critical. It will give. So the properties, input properties that we are going to give is you take E is equal to 2 into 10 to the power 11 Newton per meter square, I to be second moment of area 0.0000533 meter 4, and then L is 3.5 meter. Okay. If you take and then you substitute, okay, then I will just I am removing it, but then this matrix is being, then this matrix, the term I am just writing with this, if you substitute, then what you are going to get is basically, let me write it down. So 1.26 into 10 to the power 7, and then minus 5.42 into 10 to the power 6, and then minus 6.32 minus 6.32 into 10 to the power 6, and then 0, and then those things you can write down. 3.10 into 10 to the power 6 minus 5.42 into 10 to the power 6, 3.79 into 10 to the power 7, 1.26 into 10 to the power 7, and then lastly 2.53 into 10 to the power 7, and all these things is symmetric. Okay. Now, if you write it and you find it for the eigenvalues, solve for its eigenvalues. So solve for eigenvalue, solve for its eigenvalue, for its eigenvalues. So eigenvalues will give you, the eigenvalue will get P critical. Let me write down 4.44 into 10 to the power 5, 1.11 into 10 to the power 7, 2.0 into 10 to the power 7. You can use a MATLAB command, okay, it will directly give 4.10 to the power 7. So the fundamental critical load is important. So this is, you see that all others are increasing, you see that, okay, and then the vector, if you write 0.3660, 0.9255, 0.0870, 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. 0.0443. This is the other modes I am not writing. So these are the first. This is the first mode shape corresponding to the fundamental critical node, right? Fundamental node. Huh? So this mode shape we are going to plot. Okay, so when you are plotting it, you will see that let us plot it how it look like. Okay, so here so first one is what was the degrees of freedom. This is theta 1, theta 2, this is theta 1, this is theta 2, this is W, and then this is theta 3. So the first one is 0.366. Okay, so if you can recall that was the choice of coordinate system. So anti-clockwise was positive. So here, anti-clockwise positive means here it should have been something like this. Okay, because this rotation is positive. Okay, 366. So here it will have something like this. Okay, okay. Now what about next one, theta 2? Theta 2 is basically sorry, W is 0.0870, right? No, I think W2. I think here we have put W2 first, right? Please see that. Theta 1, W, theta 2, right? Something like this. Theta 1, W, theta 2, and theta 3, right? So then here W is positive. So here it will come to this direction, right? So it will come to this direction. So this is 0.9255. Okay. So it is coming here, huh? And then the rotation here, theta 2, that is what? Positive. It is also anti-clockwise, right? So anti-clockwise means here, if we consider this one, anti-clockwise. So from here, it is coming anti-clockwise, and here it is anti-clockwise. So here it will be something like this, maybe. Here it is, your things are going there here. So from here it is going anti-clockwise. It will go like this. And similarly here it is anti-clockwise. So it will go like something like this, right? This. Because here this 90-degree angle need to be maintained, right? So here what we can see, here it will be something like this. Okay? And then there it is something like, now here it will come there, and there theta 3 is negative. Negative means what? It is clockwise. Clockwise means what? Clockwise meaning, it will come something like this, clockwise, right? From here it is like clockwise, right? So here it will go, and this will come there. This one is going to be minus 0.0443, and here it is. This one is, this rotation, this one and this rotation, these two rotations are same, and this is 0.0870 theta 2. Okay. So this is mostly, this is the way it will look like for the buckling mode. Okay. So then from here it will go something like this. So here, okay, this one. So this is the buckling mode. First, anti-symmetric buckling, right? Anti-symmetric buckling mode. Now, what will happen, if it is symmetric? Okay, then I will just write down the symmetric one. What will happen for the symmetric one? Symmetric one, the stiffness matrix, let me write down K plus Kg. Okay, here if you write, I am writing the values, okay. So the values will be 1.26 10 to the power 7, they are 6.32 into 10 to the power 6 0, okay, and theta 1, theta 2, theta w, theta 1, theta 2, w, theta 1, theta 2, w. We have 6.32. Now, here if you solve for the eigenvalues, the critical load here for symmetric mode, for symmetric buckling mode, once a critical load, I am just going to write it down. So it is 6.267 into 10 to the power 5, 1.44 to 10 to the power 7, 5.46 into 10 to the power 7, okay, and the eigenvector, not all eigenvectors, there will be 3 eigenvector, but I am going to write only the 2, okay, only the first one, okay. This is 0.5414 minus 0.5459 and minus 0.6395. So now, once again we can draw the buckling mode for the symmetric one. So the buckling mode for the symmetric one, like antisymmetric, we can draw. So here you see that, theta 1 is anticlockwise, W, this one, the way we have written, it was, I think, theta 1, theta 2 and W, right? So theta 1, theta 2 and W. So W is downward, so this is coming down and theta 1 is positive, theta 2 is negative. So it will be something like this. This is anticlockwise, and here it is, and then here it will come down like this. Okay. Here, of course, it will be like rotation 0, and this deflection is nothing but minus 0.0443, minus 0.0443. This is clockwise rotation. This rotation is this is basically 0.363660. Oh no, sorry. This is minus 0.64, minus 0.6395. This one is 0.54154, 0.5414, and this one is negative. This one is clockwise, and what this value is minus 0.5459. Okay, so something like this, something like this. Okay. So do you see now? The important part here is basically you please note that the fundamental the lowest critical load for symmetric mode is this, and for the antisymmetric it is this. So which one is more critical? The antisymmetric one is more critical because this is lower than this. You see that? So antisymmetric mode, at least for the given frame, is concerned, as far as the given frame is concerned, the lowest critical load is given by the antisymmetric mode, right. So, please note down the critical load as well as the respective buckling mode set. Okay. Now, higher buckling mode set could have also been drawn. I didn't do it. Okay. So, this way you can solve the problem. Now, you can write a code here. The code can perform. I mean, of course, you have to have the approach is similar. Only thing is that the way in finite element analysis you have learned to find out the stiffness matrix. Similarly, you have to find out the geometric stiffness matrix. Okay. And then you can solve the eigenvalue problem. Okay. And if you have a finite element code written, you should know, have you coded anything, any finite element thing? Have you coded? If you code it, then you can, the only little, challenging part in the coding is the doing the assembly of stiffness matrix. So, from the element level stiffness matrix, identifying them and putting them right place in the structural stiffness matrix, that is why it is challenging, little involved, otherwise it is very simple coding, right. So, I hope I am not explaining that one, but there need to be one loop over element, one loop over degrees of freedom, one loop over the node, element node, another loop over the degrees of freedom. Then, because you have I and j, two indices for the stiffness matrix, you will have another one a nested loop over node and degrees of freedom. So, there will be total 1, 2, 3, 4, 5 loop, okay, for performing the assembly of stiffness matrices. Okay. Only single loop over the element, but there will be two loop over the node and two loop over degrees of freedom. Okay. And you need to give the input as the nodal connectivity. First, you have to give the element connectivity. So, each element is connected between which two node? You have to first do the discretization of structure. So, each element is connected with particular node, right. So, when you are picking up any element, you have to identify which element is connected with which node. So, that means you need to have a connectivity array defined while doing the computer programming, okay. And then you also need to give the coordinate of the individual node, because depending on that you will find out a length. Here we are not discussing further, but you have to do from local coordinate to global coordinate system transformation, that those things we have learned in your finite element course. So, those things I am not doing, but the same thing, the way geometric stiffness matrix is derived, you have to have this geometric stiffness matrix. Okay. Now, I will just show one more thing from the previous class. You can recall that geometric stiffness matrix does not show all the, at least the way we were deriving for the beam, not showing the rigid body modes. It was showing one rigid body mode, but another one was not, because of some reason that I have explained in the previous class. Now, I will show you the role of this geometric stiffness matrix in nonlinear analysis. Okay. So, what I will see that geometric stiffness matrix becomes a part of the tangent stiffness matrix as you require in nonlinear finite element analysis. Okay. But please note that the nonlinear, when we do nonlinear analysis, nonlinear finite element analysis, there are also additional component comes. Okay, that's what I will go. What is the role of geometric stiffness matrix in the tangent stiffness matrix? So, strain energy is what? Strain, potential energy is strain energy minus work done, right? So, strain energy, potential energy, we can write this is sigma, right? And epsilon, right? dV, right? Minus, the external load into delta, right? That is how we write the potential energy, right? Isn't it? So, when you do this minimization of the potential energy, so here what we will write, that epsilon is, one will be the linear stiffness, another will be non-linear stiffness. When you do nonlinear analysis, this is the linear stiffness and non-linear stiffness. Okay, so linear stiffness, linear, and this one is non-linear stiffness, non-linear. So you can recall what I write, epsilon ij is equal to u I comma j plus u j comma I plus u I comma k u j comma k, something like that, right? Oh, sorry, k comma I k comma j some. So this is the linear part and this is the non-linear part, right? Linear part and this was the non-linear part, because it's the product of this gradient term, displacement gradient term. Okay. So now, when you are doing the finite element analysis, we have learned that linear strain can be related to non-linear strain by using this B matrix, right? Strain displacement matrix. Whether the non-linear term, if you see, that you can also point out another non-linear, BL is a non-linear one, okay, B0 and BL, okay. So now, when you are coming back here, you see, you want to find out the, R, when you del pi by del delta, okay. So, or I will come there later, let us just write here, integration over V, epsilon is nothing but, you can, combine the two, so B bar into delta, and B bar is nothing but B0 plus BL. Both the linear and non-linear, okay. So sigma transpose, and epsilon is B bar and delta dB minus so find out some residual, okay. So del pi and del delta, when you del delta, when you do here, it will be sigma transpose B dP minus F, okay. Now you see, now what will happen if you, so this is the residual force we are, from the Castigliano theorem we are getting it, okay. So we are going to take an increment of this residual force, okay. Now we write down in nonlinear analysis. So dr, if we take differential of this, then what will happen here, you will see that this one will be sigma transpose, d b, dB dV, and you have written it, right, this one, right. So I can remove it, so and then plus integration V d sigma transpose B dV minus dF. F means externally applied load. Please note that F is the nodal load, externally applied load. F is the externally applied load, right? Applied load. And then here what we can write? Please note that. So here the strain displacement matrix consists of a linear part and a non-linear part. So if we take the differential of the total stress matrix B bar, okay, B bar, this is B bar, okay, B bar, this is B bar. What is going to happen? That D B bar matrix differential will be, since it is linear, this will go. only thing what will stay here will be dBl, right? Isn't it? dBl. So for nonlinear part, one whatever. So I'm just writing it sigma transpose, and here I'm just writing d alpha dB, right, plus integration b. When I'm writing d sigma, bar, d sigma is nothing but what? You can write, sigma is E into epsilon, right? So then d sigma is E into d epsilon, right? So where you can write here, this is, is and d epsilon is nothing but, E b delta, and please note that this is non-linear, right? Because if you take differential, differential of the linear part of strain, then it will be 0. So non-linear part will be there. So here I can write E, this is E, this is BL, this is delta, and then B dB minus dF, right? What do I see here is that this part, this part is the one. You see that this one contains the stiffness, stress, as well as then dBl. You can also later you can simplify it dBl. Okay, dBl it can definitely be expressed dBl is equal to dBl can also be expressed in terms of something like this. Okay. This one is nothing but the tangent stiffness matrix, geometric stiffness matrix. It's a function of the stress. And here you can then rest of this part it will be consisting of four elements. One will be, of course, one will be K0, E, B0, E, B0, dB. Another one will be B. L transpose E BL. Another one will be B0 E BL dB. And another one will be BL E BL dB. So this additional thing will come from this, okay, and then these are the incrementally externally applied load dF, okay. So you see that the total this dr is nothing but this is KT into d delta. E2 into d delta is nothing but dF. So externally applied, okay. So here tangent stiffness matrix, a part of tangent stiffness matrix is consisting of the geometric stiffness matrix, and then there will be some additional terms here, okay. Some additional terms will be there here, okay. So what is important to see here that when we do the nonlinear analysis, the tangent stiffness, the geometric stiffness matrix plays an important role over there, okay. And that's what basically we are getting here, okay. So that's what I want. The point I wanted to make here is that geometric stiffness matrix become a part of the tangent stiffness matrix for nonlinear analysis, but it is not everything. There will be additional stuff other than the geometric stiffness matrix, okay. And when we are doing, because when we do a fully nonlinear analysis, fully nonlinear stability analysis. We have to solve for the whole system through a nonlinear analysis. Okay. Geometric nonlinear analysis. You have to do full analysis. But when we are doing linearized stability analysis, that means where we are linearizing the system of equation, only in a system equation to include only the linear term, that's why it is leading to a eigenvalue problem, and that's what we are truncating this part. We are truncating this part, and we are just making the material stiffness matrix, linear stiffness matrix, and then geometric stiffness matrix, and then solving the respective eigenvalue problem. Okay. So do you see that how the linearization is done? So when you are doing the linearization, only this part will be there. See, this part is the linear stiffness matrix. Okay. So K plus K sigma will be equal to 0. Okay. If there is no externally applied load, dF is 0. So that becomes the linearized, stability analysis, and we neglect this part. These are nothing but nonlinear terms. Okay, which are otherwise need to be included for a nonlinear stability analysis. Okay. So we must understand and appreciate the regime of analysis. How we are doing the analysis? We are basically doing a linearized, analysis when we are solving the eigenvalue buckling problem. A eigenbuckling problem is basically linearized stability analysis. But if you include the nonlinear term, then you will have additional stuff. Okay. Now, of course, when we do nonlinear analysis, we use some special, you have to evaluate this KL nonlinear. That's not difficult. In a nonlinear analysis, people will explain to you how to find it out, but it's not very difficult. It's kind of okay. Yeah? So with this, I will conclude here the portion for the matrix method, or finite element analysis for the stability analysis. Okay. Okay. So now what we are going to do? We are going to study the buckling of plate. Okay. So all of you have already studied the buckling of the bending of plate. All of you have studied, right? What is a plate? Plate is a structural element which primarily carries the transverse load, and its one dimension is much smaller comparing the other two dimensions, right? So essentially, its mechanics can be condensed into in terms of displacement, which is concentrated at its middle surface. Okay, so all the kinematics of deformation can be essentially expressed in terms of deformation of the mid surface, right? So that's where we define a plate, right? And this we can take as x, this one we take as y, and then downward we can take as, it's right-handed coordinate system, right? This one, the dimension we can take a for the x dimension, and then for the b, the dimension of y, right? Things like that, right? Now all of you are aware about the bending of plate, right? And then you have derived the governing equation, right? What was the governing equation? The governing equation was W square W xy is equal to q xy upon d. But W is nothing but vertical deflection, of course downward deflection, and q is this is the load being applied, that is q xy, and d is the flexure rigidity, and d is the flexural rigidity. D is equal to Et cube divided by 12 into 1 minus d square. The flexure rigidity of plate, okay. And nabla, this operator, nabla square, it is nothing but a, del 2 del x2, Laplacian operator plus del 2 del y2, and then if you just write it, it is del 4 w del x4 plus 2 del 4 w del x2 del y2 plus del 4 w del y4 q x y. That was the governing equation for the plate bending, right? How you derived it, that you all of you just did it. I can briefly recapitulate. I mean, two ways you can derive it. One is directly integrating the starting from the equilibrium equation, as you have learned in continuum, right? And integrating the equations over thickness and okay. Another way is to show the stress resultant over here, and we can go there, right? Which approach did you follow in your theory of plates and cell? Huh? You have directly started from the equilibrium equation as you have learned in mechanics, or you have equilibrium equation. Yeah. So the way we have derived, bending a plate, I will briefly recapitulate. So if you can recall that, assuming this is the plate, so you see, so this is positive x, this is positive y, and this is positive z. So you can recall that, that was like double arrow we have used, right? One second. So we are using double arrow for the bending moment mx. So here it will be, this is mx plus del mx by dx to dx, right? And then here it will be in opposite direction because this is positive phase, this is negative phase. You understand, na? Positive phase in positive direction of x, this is positive. Okay, that's what. And then this is negative phase because it being normal to this is negative, right? Similarly, here it is my del my del y dy, and here it is my. Then also we give that torsion, right? This is mxy plus del mxy del x, right? And this one is mxy, and then myx. Please note that myx plus del myx by del y into dy, and here it is myx. So these are the bending moment, and then please note that there are too many bending moment per unit width, mx, my, and mxy. Mxy and myx is same. Bending moment per unit width, my is the bending moment per unit with respect to x axis, y axis, and mxy and mxy are the torsional moment, right? And then you can also derive, this is the bending moment, right? And also you can also this we are showing the moment, and then we can also show the forces. The forces, how we can show? The x, this is positive x, right, and downward h positive, so this is qx, plus del qx, del x, right, and here it was qx, then here it was qy, del qy, del y, del y, downward. So from there you can do the force equilibrium and then you can do the moment equilibrium. When you recall the force equilibrium will give you, the equation del qx by del x plus del qy by del y is equal to q plus qxy is equal to 0. This is moment equilibrium, right? And similarly you can get the this is force equilibrium along vertical z direction, and then qx is del mx by del x. If you write here, from here you will see, qx, this one you can understand, this is the force equilibrium, right? Now, if you do the moment equilibrium with respect to x-axis, with respect to y-axis, then here you see that del mx or del x, right? Here, right, this one plus del mxy plus yx by del y, right? Plus then this one plus qx is equal to 0, right? This, and then similarly you will also get mxy by del x or del y plus qy is equal to 0. So you just combining everything, three equation if you combine, you substitute qx, this expression here, okay, and then you will get what you, right? And if you can recall, by, we can derive what is the mx. Mx will be, this is nothing but integration sigma xx z dz, and this is minus t by 2 to plus t by 2. And when it is plate bending, it is basically the generalized plane stress, right? Generalized plane stress, especially when we are discussing this plate theory, it is thin plate theory, which is Kirchhoff's plate theory, right? There is no shear deformation, so plane sections remain plane after bending. So sigma xx, if you can recall, can be expressed as minus t by 2 to plus t by 2, and this is z divided by 1 minus mu square epsilon xx plus nu epsilon yy z dz, and here epsilon xx epsilon yy and epsilon xy, epsilon xx, we can recall epsilon xx was what? It is nothing but del u del x, and u is nothing but del what? Minus z into theta, and theta is nothing but minus z del w del x. So theta x basically, okay. So minus z del 2w del x2. Similarly, epsilon yy can also be written as, why this is happening, right? Because if you can recall, so like this, isn't it? So plate, so bending moment is like there, okay. So you can see this normal section, so here it is coming there and this is in there. So that's why this is minus sign, right? So similarly, so from there mx, if you combine these two, so from mx here you will get mx is nothing but 1 minus, minus, it is nothing but d into d2w dx2 plus mu into d2w dy2. This is the bending moment curvature relationship, and then similarly you will get MOI is, minus d, minus d d2w dy2 plus mu into d2w dx2. Please note that I am there might be some inconsistency in terms of sign, but that sign will, then mxy will be 1 minus nu into d2w dx del. So you see that. So for the moment it is direct curvature d2w dx to nu 2w dy2, and because there is two-way bending, that's why this nu term will be there for the Poisson ratio, and for the cross curvature related to the torsion in unit width. Okay. So if you take this and then substitute everything, then only you are getting the equations, which is del square wxy is nothing but qxy, qxy, and here is d. This is the governing equation. When you will get, when you will substitute everything combined. So this is this is the way to derive. But another way to derive the plate bending equation is basically, we do not require to discuss all these things. You just start with the equilibrium equation. So the way you can directly derive it, is, you see that sigma ij comma j is equal to 0. So you can see, so sigma xx plus del sigma xy del sigma xz is equal to 0. Okay. Now, if you multiply with z, multiply that with z, okay, and integrate it. So, over z, when you are integrating it, you will see that here you take del x of integration sigma xx z dz, and then you multiply minus t by 2 to plus t by 2. Here is see del y integration minus t by 2 to plus t by 2 sigma xy z dz, and then last here it is basically, when you are integrating it, here you have to be little careful, So first function integration of the second minus whole integration derivative of the first derivative of the first integration of the second. Okay. So here you see, this is nothing but sigma xx multiplied by z dy is nothing but what? This is nothing but mx. So del mx del x. This is what? This is nothing but mxy, because what is happening, you see that, there are stresses, you are taking the moment, okay, mxy, and then this, in the top and bottom surface, if there is no traction, this will vanish, and sigma z dz is nothing but qx. So do you see that this equation is nothing, but this equation is leading to this equation? Do you see that? Right? This equation is coming directly, we can obtain without going into anything. We can derive that thing just from the what? Equilibrium equation in that we have learned in mechanics, right? Directly multiply the equilibrium equation with z and integrate over the thickness, and we get this equation. Similarly, if we integrate the same equation which indicates the equilibrium along y-axis, similarly you will get the second equation. This one equation you will get, and then if you integrate the equilibrium equation over z, you don't require to multiply with z, then you will get this equation. So you see the three equilibrium equations, and then now all this this relationship. So then we substitute from this into there, and then assume the plate kinetics, all these assumptions, you can directly go to the governing equation. So you see that there is two different ways to derive it. Okay. Now, having the plate bending theory known, we have to go to one step ahead, because we now want to study the stability of the plate, right? So stability of the plate, what we have to do here, we have to consider, see all these things when we are doing, we are considering equilibrium in the undeformed configuration, unperturbed configuration. But when we want to study stability, we have to consider equilibrium in the deformed configuration. We have to consider a priori deformed configuration of the plate, and then you will. Once again, when we write down the equations in the deformed configuration, some additional component of stresses will come. That we will see. Once again, that can also be done directly from the considering the force resultant in unit with, or you have to consider the stresses, this equilibrium equation, but not this. We have to now this is the Cauchy stress tensor equilibrium equation, which basically in the deformed configuration. Now we have to distinguish between deformed and undeformed configuration. So you have to invite additional equilibrium equation where this distinction is made. That's what we have to consider the finite deformation theory. And in finite deformation theory, the equilibrium equation is written in terms of alternate stress measure. First Fibonacci stress measure, second Fibonacci stress measure. That's what we are going to discuss next class. Okay, for this today let us stop here. Thank you.